So welcome to the fourth lecture of the course, Concurrent Algorithms and Data Structures. So first, some announcements. So as I told you before, the reading list is already uploaded to the student portal. The slides are uploaded. The videos are available on the usual place on YouTube. So now you have the first three lectures of the course. And for PhD students, everything is available at the usual place. So now a couple of remarks about the reading list for the book that I have provided. First of all, it concerns the first edition of the book. In fact, the second edition, as far as I know, it's still not available in the market. So it refers to the first edition of the book. And furthermore, in this first edition, at least, there is no notion of section or chapter. I mean, they have numbered the sections of the chapters, whatever you call it. So now in the reading list, I say section, but you can interpret it as chapters if you wish. So a couple of changes to the schedule. So I think the lab comes too early. We still need to cover some material in the lectures, and then I'll give you the lab and the assignments later this week. But the lab on Friday is cancelled, so there is no lab on Friday. And instead, the second lecture next week, which is on Thursday, will be a lab rather than a lecture. So this means that in principle, we move the lab from this Friday to next Thursday, and we cancel one lecture, which is the one which is next Thursday. So no lab on Friday, one lecture on Monday, and then a lab on Thursday next week. And this I will announce on the student portal, and of course I will send a mail to all the students, but so that you know. Again, if we go to the outline of the course, we have done the overview, and there, in principle, we considered specifications, and we considered two classes of specification or specification properties, safety properties, in which we state, let me see, there is some question. Do you think it will be updated in the schedule? I don't understand what you mean. You mean a student portal? No, not explicitly. I will send a mail to you in the student portal with the same information. But the schedule will not be updated. Usually, they do not update the schedule. Okay, so what we said was that we have safety properties where we state that nothing bad will happen during the execution of the program. And we said that this amounts to checking the reachability of some bad states, where the bad states are the states that violate the given safety property. So this was one class of properties which we wanted to analyze for the programs that we considered. A second class was liveness properties, in which we state that something good will eventually happen during the execution of the program. And this is for non-trivial reasons possible to translate to checking the repeated reachability of some good states. That is, you are given a liveness property, you can construct a finite automaton and characterize some states of the finite automaton to be good states, and then reduce or express the liveness property as having infinite executions of the finite automaton that visit the good states infinitely often. But this is not something that I will cover during the course, as I say. But we do cover safety properties and liveness properties, and we say that these two properties, they complement each other. So safety properties means that nothing bad will happen, while liveness property means that the system will progress. And we say that an important motivation for dealing with liveness properties was that you could almost always implement a system which is passive, it doesn't do anything, and then therefore it trivially satisfies any given safety properties because it will never reach any states in the first place, let alone any bad state. So liveness properties ensure that there is some progress, something good will happen, something meaningful will happen during the execution of the program. Okay, so this was the main message from the overview. And we said that the particular safety property that we will consider in this course is so-called linearizability, which we will define next week, in fact, when we start dealing with concurrent programs. So this was the overview, made very short. So then we considered abstract data types, and we said that we will use abstract data types as a tool to state safety properties, as a tool to state linearizability properties. So in principle, what we will say is that if you have a concurrent program, then we consider its histories, as we will define them later. And then we say that there is a corresponding sequential history or a corresponding execution in which the program is executed sequentially, such that such an execution respects the behavior implied by the given abstract data type. And for abstract data types, we went through the definitions, and then we instantiated the definition for sets, queues, and stacks. So this was the example for sets. We said that the definition of an abstract data type is a set of states, an initial state, a set of method names, and a set of rules. So in the case of sets, we say that a state is a set of integers, but we say that this is not a restriction. This is just for convenience. We work with integers or natural numbers, but a set can be defined over any domain. So we say that a state in the abstract data type set is a set of integers. This is one example of a state consisting of 2 and 5. And then the initial state is the state where the set is empty. The methods that we allow in this particular definition of the abstract data type set, these methods are add, in which you add a new element to the set, and you fail if the element is already there. Remove, where you remove an existing element in the set and fail if the element is not there. And contain, which checks for the membership. So given an element, a constant, it checks the set and sees whether the element is stored in the set or not, and returns true or false correspondingly. So these are the method names or the methods that we used to define our abstract data type set. Now the rules, each rule was a guarded command. So this was the general form of a rule. So you had the guarded command. So this part was the command, and this part was the guard. And the command does two things. It starts from some state, it performs some operation, and as a result, it produces a new state. So it has a source state, which is the start on which you apply the operation in the command, which in this case is the particular operation where you add the element X successfully to the set. And accordingly, the rule tells you that you add the new element X to the set S. So this is the target state. And now if you look at the operation, which is part of the command, you see that it consists in turn in three parts: the name of the operation, the input value, and the output value. And we say that some of these may be missing, the input or the output, and we saw examples of that. Now all this can be done provided that the guard is satisfied. And now the guard is some condition on the source and target states. And we say that we mostly work with conditions on the source states. So this was a typical example of a rule. And the important observation was that at this abstraction level, where we have abstract data types, An operation corresponds to the atomic execution of a method. So this means that in the operational semantics of the abstract data types, what we do is that we take a state from which we want to apply some rule. And if the state satisfies the guard, then we can perform the operation. And this operation immediately updates the state to the target state before we perform the next rule. So this is what we mean by atomicity of operations. And this allows us to define these data structures in a clean manner. And then it will make it easier and more intuitive when we analyze the behavior of programs to see whether their behavior satisfies the abstract data type or not. So now in the case of sets, we had 6 rules that we went through in detail. So I'll not do it again here. But an important remark here was that each rule corresponds to an infinite set of rule instantiations. And this is because you have so-called free variables in the definition of the rule, S and X in this case, for instance, which means that you can instantiate S and X with any values, S with any set over the set of integers and X with any integer. And provided that this instantiation satisfies the guard, then you can apply the rule to the given state and generate the corresponding target state. And we gave some examples of instantiations of the rule add successful addition of X. For instance, this is one instantiation shown here. If you take S to be 2, 5, 4, the set, and you take X to be 7, then you indeed can apply the rule because 7 is not member of the set, 7 is not in the set here. And as a result, you get the target state in which you have added the 7, which is the X here, to the target state to obtain the to the source state to obtain the target state, as you show, as you see here. So in short, an abstract data type is defined by states, initial state, methods, rules, and the operational semantics, while can be defined formally, but informally, is defined by regarding as rule as an infinite set of instantiations. And now you can define the notion of traces. And we say that in a trace, what we do is that we start from the initial state and we apply a sequence of rules changing that are allowed by the guards and changing the state from source to target accordingly. And then once you have performed a finite number of steps, any number, you collect the sequence of operations that you have generated, and in such a way you obtain a trace. So this is the situation here. I start with S0, which is equal to S init, which is the initial state. I apply some rule, which allows me to execute the operation op1. As a result, I obtain S1, and then I repeat the procedure, applying op2 to obtain S2, and all the way until I apply op_n to obtain Sn. And now I just collect these operations here and I obtain a trace. So a trace is a sequence of operations that arise from repeated application of the rules starting from the initial state. And we went through some examples. For instance, we started from the initial set as implied by the definition of a trace here. And then we had this notion of time axis, which records the order in which you perform these operations. So for instance, from the initial state, which was empty, we could perform the rule here, which says that if 2 is not in the set, which was not when it was empty, then I could add X to the set and perform this operation, which is the operation recorded here. And now from this state here, I can do add 5 and add 5 to the set for the same reason as before. And add 2 false can be done also because I'm trying to do add 2 to the set, and 2 is already in the set, which means that I can perform this operation and not change the state. I can remove 5 from the set, because 5 is in the set, so I can remove it. Like that. Here I cannot remove 3 because 3 is not in the set. So this operation is not allowed. So I'm not allowed at this point to add this new operation to my trace. So all the operations that I add to my trace are those that are enabled according to the guards from the particular states from which I'm trying to apply the rule. And by continuing like that, we can generate a trace like this, an execution of the abstract data type set like this. And in such a manner, I obtain a trace by collecting all the operations. So this is a trace of the abstract data type set. And we gave some examples of traces or sequences of operations, which were indeed traces belonging to the set of traces of the abstract data type set. And we also gave some examples of sequences of operations which were not, and because they violated the conditions of applying the rules, so they violated the guards, the corresponding guards from the particular state from which we were trying to apply these rules. And we also said that, just to repeat it, the fact that all these operations that we are generating as parts of traces, they are performed atomically. So you see that I perform the full operation before I proceed to apply the rule or another rule to generate yet a new operation, etc. So this is the notion of atomicity. And then we proceeded to queues and we repeated the procedure. We say that again, we have a set of states. So in this case, I represent the state of the queue by a word over the set of integers. So this is a particular queue state. You see that I have a word of integers. The initial state is, in this case, is the state where the queue is empty, that I have the empty word epsilon. The set of methods in this particular definition, I had enqueue and dequeue. Now in the first assignment, which I will upload later this by Friday, latest, you will be asked to define the abstract data type of an extension of this notion of a queue that we have here in a way that I will describe in the assignment. Anyway, in this particular definition, I have 2 methods, enqueue and dequeue. And the set of rules consists of 3 rules, 1 of them for enqueue and 2 of them for dequeue. The enqueue takes some state W, which is a word, and append to the end of the word, the right-hand side of the word, an element A, which is to be enqueued. So enqueue has 1 input parameter and no output parameter, as we say, in which we append the input parameter to the end of the current state of the queue. So W appended with A. DQA says that if you take some element A, some integer A, then you check whether the A is at the head of the current state of the queue. And it's only then you can perform such a dequeue operation. If this is the case, then the rule is enabled, and as an output value, you get back the value of A. And as a new state, you obtain W, which means that you have dequeued A, you have fetched and removed A from the state of the queue. Finally, if the queue is empty and you try to do a dequeue operation, you still have some output, but the output value is some particular value, which we call star in this case, that just indicates that the queue is empty and you do not change the state of the queue. So these are my guarded commands for the rules, and observe that here we just have commands and no explicit rules in the definition. Although there are some implicit rules, for instance, in the dequeue operation, you can output A only if A is at the head of the queue, and you can output star only if the queue is empty. And we reapplied the definition of traces by starting from some initial state, that's an empty queue, and then applying a sequence of rules and collect the sequence of operations. So this was one particular scenario where we started from the empty queue, we dequeued star and then enqueued some elements and then dequeued the first one, and concluded that this indeed belongs to the set of traces of a queue. And again, we give some examples of traces or sequence of operations that belong to a queue, and sequence of operations that do not, because they do not respect the operational semantics of queues as defined by the rules in the abstract data types. And again, the thing to observe here is that all these operations are considered to be atomic. When you do an enqueue or a dequeue, you have to wait until the operation has been concluded before you proceed to apply a next rule. And then we did the same thing for stacks. And again, for stacks, we had a set of rules. We had two operations, push and pop. A state was, again, a word of integers, or the set of integers. The difference was in the definitions of enqueue and dequeue, which we call now push and pop, mainly for historical reasons, because in the classical theory of automata theory, these objects or these operations are called push and pop. So now a push will push some element A to the head of the stack, which is the left-hand side in this particular definition. So, and we, as you recall from the first lecture, in a stack, we always operate on the topmost element of the stack. So this means that if you push an element, then you push it to the top of the stack, and you pop an element, then you pop it from the top of the stack, and you remove the element. You see that I both add and remove elements from the same side of the stack, which is the difference between stacks and queues. And from the point of view of computability theory, this simple difference will have dramatic consequences. For instance, checking reachability for finite state programs operating over stacks is decidable. Well, it's not decidable if you have queues, but this is beyond the scope of this course. Anyway, so for a stack, we pop and push from the same side. For a queue, we push from one side and pop from the other side. And again, we have this particular operation to indicate that the stack currently is empty. And having these rules, again, we can start from the empty stack, which is the initial state, and apply some operations. And in such a way, obtain a trace tau in which all the components are atomic operations. So the message to take from this part of the course is that a trace is a sequence of atomic operations that respect the operational semantics of the abstract data type. Okay, any questions up to now? Okay, so then we started with sequential programs, and we say that the plan was as follows. So first we define the notion what we mean by a program. Then we consider sequential histories. These are particular refinements of traces in which the operations are not atomic anymore, but in which any invocation is followed by a response. And then we describe how to transform histories to traces by collapsing the calls to operations. And then we started with an example of implementing a set. And the main message here will be that from programs, you can go to histories, from which you can go to traces. So we are going up in the abstraction level. Okay, so we start with programs, and we say that a program, to start with, is just a black box. If you wish, like an abstract data type, but in contrast to abstract data types in which operations are atomic, in programs, the operations are non-atomic, meaning that in principle that an operation takes time. And this means that from the modeling point of view, you view an operation as two events, an invocation and a response. And this is important because now I can view the program as a black box, which has some input from which it takes the invocation event, and from another port, the output port, from which it outputs the result, if any. so here we have an example of a program which, as black box, we don't know what is inside the box yet, but presumably it implements a set. And in such a case, it takes an invocation, and usually the invocation event takes the event name and the input value, if any, and it outputs as a response, it outputs, the program outputs the output value. You see, name, input value, invocation, response, and then output value. And in such a way, we can say that an operation, such an operation, corresponds to two events: input and output, invocation and response. Okay. Okay, so now taking this model, we can now generate what we call histories. Again, we have the time axis. Now we record what we see from the interface of the program. So in this particular case, this corresponds to the invocation and the response that I just explained to you. And now we say that the interval, this interval between invocation and response, we call it the call, a method call. So now, this is a refinement of the notion of an atomic operation that we had in the case of a trace. So we can now give more inputs to the program and we will get more outputs. So here we have given the input at 5, from which you obtain true from the program. Contain 4, we obtain false. Remove 2, we obtain false. So you see that this is a program that is working here. We give it some input, we get some output, and in such a way we obtain a history. So history is just a sequence of invocations and returns, in contrast to the notion of a trace, which was a sequence of atomic operations. And this particular history that's generated by sequential program is sequential, meaning that method calls do not overlap. So you see that each method, inputs and outputs, terminates before you call the second method. And this is consistent with our intuition of a sequential program in which the program carries out its instructions sequentially, one after the other, without any overlap. So each invocation is followed immediately by a response. Now, such an history is easy to collapse to a trace. In fact, this was the second step that we did by just merging each invocation with the corresponding response, and in such a way obtaining an operation. This was exactly what we called an operation when we defined traces in abstract data types. So we collapse the name, the input, and the output, and in such a way we collapse the call into an operation. And by doing that to all the calls in the history, we obtain a sequence of operations, as you see here. And now, because you have a sequence of operations, this is a trace. And we call this the trace of H. So given an H, I can derive its trace tau, which I call trace of H. So you can see this as an operation on histories, which I get this trace by just taking each call, each invocation and the corresponding response, and collapsing them into one operation. So in this particular case, this is the trace of this history H. And now this allows me to define what I mean by histories of abstract data types. So if you give me an abstract data type, I can define its set of histories by saying that a particular history H belongs to the set of histories of the abstract data type A if the following condition is satisfied. If I have a history, if I have a history H whose trace is a member of the set of traces of the abstract data type. In such a case, I say that H is in the set of histories of the abstract data type A. So in this particular example, because tau is a trace of the abstract data type set, and tau is the trace of the history H, then we conclude that H is in the set of histories of the abstract data type set. So this is interesting because this means that abstract data types not only characterize sets of traces, but also they characterize sets of histories by just taking the traces of the abstract data type and taking all histories that collapse to the traces of that particular abstract data type. So this means that at the abstract data type level, we can, in principle, work equivalently with histories and traces. And what is interesting is that even for sequential programs, we can work with both. Because as we will see, a program will generate a history, and this history I can transform to a trace, which I call the trace of the program. So this is the converse direction. So at the level of the abstract data type, if you give me an history, I can transform it to a trace and call it the history of that abstract data type. At the level of the program, I will generate a history and then transform it to a trace. And that trace, I call the trace a trace of the program, as we will see. So now let's look at some examples of histories. So in fact, we did that. We look at some examples of histories of the abstract data type set and some histories that did not belong to the abstract data type set, and the same thing for queues. So now we know programs, sequential histories from transforming histories to traces. So now we will look at a particular sequential program that implements a set. Now this program is quite simple, as you might expect how it looks like. But the reason, in fact, we go through it in detail, and the reason is that this will be the basis from which we refine the code of the program and obtain different concurrent algorithms for that respect the abstract data type set. So it's important to understand the basic concepts in the sequential case, which is simple but fundamental. So this is what I was saying, is that if you have a program P, you generate a history of P by looking at the sequence of invocations and responses. And from this history, you can generate a trace. And now this trace, you call it a trace of the program. So you see that I'm working at both levels. The level of a program, I first generate a history from which I derive a trace. So the traces of P I get by taking the histories that are generated by P and applying the trace-off operation on these histories in such a manner, obtaining a set of traces, which I call the traces of the program P. At the abstract data type level, we generated the traces, and then we could refine them into histories. So there is a nice correspondence at both levels. Now, let's look at how such a program looks like. So if you look inside the black box, you see that you have different modules, each of which is hidden at the moment. And this is a particular style of program, or particular class of programs that we generate in this course. Namely, you have a data structure that is shared by these modules. Each module implements one of or a set of rules, one of them methods. So in this case, I have a program that implements a set, the abstract data type set, and therefore I have the data structure in which I store the state of the set, and I have three modules: add k, remove k, contain k, where k is the parameter to the method. And I can instantiate it to different values. So this is the method name, if you wish, and this is the input value. And what happens here is that when you invoke an operation, we choose the model to perform the operation depending on the operation to be performed. So if you had add 3, as we saw, that we invoke the module add k with the value 3, it goes to the data structure, it changes the state of the data structure, it asks the data structure whether 3 is there or not, and the data structure responds by changing its state and answering, and the answer is propagated all the way out. In such a way, we obtain the response. Now, let's look at these three modules, how they look like. So let's first look at, it's taking some time, the add. So now we have the add module that operates on the data structure. Now, what's nice with these programs is that each module can be implemented separately. So now we see how the add method interacts with the data structure. So let's look at this. So now I'm looking at the add module with the data structure. Let's remove the cover of the add. It's a simple program that manipulates something, which is the data structure. And if you look at the data structure, it is nothing but a singly linked list. So the idea here is that we have a singly linked list. The elements inside the list, they store the state of the set. These are the elements currently inside the set, 1, 3, and 5. And furthermore, you have two end markers whose keys are -infinity and +infinity. And the classical question which I get here, okay, so how shall I program this? Well, this is just to make the code simpler. So in reality, you can have two additional values, special values that you interpret as -infinity, +infinity. Anyway, we have 2 pointers, h, which is the head of the list, and t, which is the tail of the list. And these 2 pointers, they point to the leftmost element and the rightmost element in the list, respectively. So if you look inside the cell, you see that you have a key, and then you have a pointer to the next cell. And this is the same everywhere inside the list. So now we have to say what will happen if I do add k. So suppose that I have this current state of the data structure, and now I have an invocation which tells me to perform add on 4. So now the add what it should do here is that it should consult the data structure, ask it whether the 4 is there, and if not, the data structure is supposed to change state and add the 4 to it, to its structure, so that 4 will now be stored inside the list. Now this program is very simple, but you have to understand it in detail, because as I told you, when we implement subtle concurrent implementations of sets, almost all of them will be variants of this code. So by tweaking the manner in which you ask and change the state of the data structure, you will get different implementations of concurrent programs that manipulate the setup circuitry type. So here we have 2 pointers, P and C, each of which is a pointer to a node. And the idea is that P and C will travel in parallel through the list. C means the current element of the list, and P means the previous element. So initially, so this is where I am in the code. I'm at the initial instruction. P is assigned the value of h, so it will point to the same cell as h, and C is assigned to the next element. So it's always the case that C will be the next element of P. This will be an invariant of the algorithm. So this is what we do here. We assign h to P, and then we change program counter, and now we assign C to the next of P, which is here. And now we come to this while loop, and this while loop is important. What it does, and this will be always the case in all the codes that we will write, in fact, is that this while loop will look inside the data structure and see what's there. So this is the while loop that asks the data structure, that inspects the state of the data structure and asks the data structure, or updates the data structure according to the result of the search. So the idea here is that you move P all the way until you obtain a value which is larger than or equal to K. where k is the value to be inserted. So case 4 in this case, you see? So now this is what I do. So if I do here, I look at C. Is the key of C smaller, strictly smaller than k? So the key of C is 1, it's strictly smaller than 4, which means that I have moved P to C and C to the next of C, which means that I move these pointers in parallel 1 step to the right. So this is what happens in the first step of the while loop. So you see that I have moved the pointers, and now I repeat the reasoning. Is 3 strictly smaller than 3 strictly smaller than 4? Yes. So I have to perform yet an iteration of the while loop and move the pointers like this again. And now I ask the same question, is 4 strictly smaller than 5? No, which means that the while loop will terminate. So now there are 2 possibilities encoded by this if statement here. Either 4 is in the set or not. So if the value, the key of C, the current key of C, is equal to k, this means that 4 is in the set. But in this case, the key of C, 5, is strictly larger than 4. In fact, it's not equal to 4, which means that we will come to the else branch here. And the else, what it does is that it will update the state of the data structure and answers. It will answer accordingly. So this is what it does, is that it creates a new code whose key is 4 and whose pointer is not defined yet. This is the new node in which the key is 4, k, and the next pointer is not defined. But as you might expect, I define the next pointer of this cell, which is the new cell to be inserted in the list, so I have to insert it here. And the reason why I want to insert it here is that I want to maintain the sortedness of the list. So this is an important aspect. This list is always sorted. So the list stores the elements of the set, but it's always sorted. So what this while loop does for me is that to find the position, if any, which is appropriate to insert the new key in the set. So this is the position. I found the position, I create the new node with key 4, and I define its next pointer to be the one pointed to by C here, as you see, and this is what I get. And then I go to the next instruction, in which I redirect the next pointer of P and make it point to the current cell, the newly created cell, which is this thing here. So you see here, what I have done here is that now I have added the 4 to the set, and relating to the abstract picture that we have, in which we say that the abstract or the data structure will change state. This is what we mean by changing state. You change the content of the data structure, in this case by adding a 4. And finally, we also say that we should answer, the program should answer whether with the output value, and in this case, we will return true, which will be the output value. So now let's see whether we have a question. What does the list have to be? Why does that, isn't a set and ordered? Yes, you can implement it as an ordered list, but there are 2 reasons why the set should be ordered, or the implementation of a set. First of all, from the point of view of the user, you do not see whether the set is, whether your list is ordered or not. And this has to do with the notion of a specification, which we say that we have an abstract description of the behavior of the program. How you implement this is up to you. Now we choose to implement this as an ordered list for 2 reasons. First of all, sometimes it makes it more efficient because you don't have to search the whole list, for instance, as we will come to later, whether to see whether the element is there or not. This is one thing. And secondly, it is crucial when we come to the case where we have concurrent programs, because they will have different threads that are active at the same time. And if your list is not ordered, you don't know what the different threads are doing that are currently active with you. So by maintaining sortedness, you will, although you have concurrent threads, you will be able to work locally on a given part of the list rather than searching all the time and again to see whether some thread came after you and changed something, and therefore you should redo your operation. So you don't have to to roll back your operations in such a case. So there are some very elegant algorithms that use this fact. And this is what I told you, is this program generated from the model through refinement? No, I mean, this is a different problem. So what we do in this course is that we have some specification, some property, and I give you a program and I claim that it will satisfy the specification. Now, if you want to make sure that it satisfies the specification, you have to do either testing or verification. This is beyond the scope of the course. So I'll just give some arguments why this is reasonably, it's correct. But also there is the problem of synthesis, which is well beyond the scope of this course. Namely, if I give you a specification, refine the specification, obtain a program. In fact, this is still a challenge that has not been solved by the research community. I mean, there are active groups that are trying to do this, but this is a hard problem. So to make the answer short, no, the program is not obtained through refinement. I am giving you a specification, and the notions of refinement I am describing in this course are concept refinement. So an abstract data type is conceptually, or a program is conceptually a refinement of an abstract data type in the sense that I described, but doesn't mean that I have a synthesizer that if you give me some abstract data type, I can generate a concrete program for you. Certainly not, which tells you that this list should be sorted. So it's sorted for totally different reasons. Okay, so did I answer your questions, Philip and Ahmed? Yes, okay, thank you, thank you. So I think we'll take a break now, and then we will continue in 15 minutes from now. And we continue with this implementation of the program. And you see that although the program is simple, there are some things that are subtle that we need to understand already here. Otherwise, it will be impossible when you